had a good fall break, so we have 8 more weeks of the semester left. So 8 more weeks of class, which amounts to us 2 more tests, 2 more quizzes, and a final that replaces a low test grade. So that is where we are at, and a couple of more labs. I think about 3 or 4 more labs that are left. So let's try to finish this off on a strong suit and a strong note. Chapters 15, chapter 16, chapter 17, and then chapter 18. And then we are done. So that is where we are at. So let me start off with some announcements here. The first announcement I want to make concerns the lab. So the lab on solubility product, which was last Wednesday's lab, I'm going to extend it, and it's going to be due next Wednesday. Okay, the lab that we did last Wednesday is going to be due. Well, you can turn it in this Wednesday, today, right? Today's Wednesday. You can turn it in today. That's perfectly fine. And I think some have done that, but I'll accept it till next Wednesday. So that was the lab we did last Wednesday, technically due today, but because of fall break, trying to get everyone back into the swing of things, we'll make it due next Wednesday. And then the lab this week is a problem set, acid-base chemistry problem set. So you can work together and turn that in 2 weeks. So work with your lab groups, watch the video that I posted on Canvas, and yeah. So not due next Wednesday, but the following Wednesday. Following Wednesday in 2 weeks. Okay, so you have 2 weeks to do those problems. Okay, work together, work with your lab group. Don't turn in the same thing. Everyone do the problems. It helps you learn. And I do want to tell you there are a couple of things you can skip. Okay, you can skip in this problem set. In this problem set, you can skip complex ion formation. So you can skip complex ion problems. Okay, so K of F. Alright, so lab due today, but you can turn it in next Wednesday. Today's lab is not going to be done in the lab. Okay, it's problems. So work together. It's a lot of problems. So you want to start off with your group. Watch the video that I posted, and we'll be doing 2 weeks. Okay, and in that problem set, you do not have to do anything involving complex ions. So yeah. So any questions or comments on this? Right, so lab today is not a lab, it's something you do at home. A lot of math problems, a lot of titration problems, in fact. Okay, so something I've not gone over, but I will go over when we talk about chapter 16. So do not have to come to lab today, but I definitely want you to start those problems because there are a lot of problems. Okay? Can I get your word on that? Yes or no? Okay, very good, thank you. And that's it. That's all I have. Start working on quiz 3. Whenever test 3 is going to be due, and work on homework 15, I'll give you a due date for that. Okay, those homework 15 practice problems. So let's just get back into our lectures here. All right, so work on quiz 3, homework 15, lab. I'll give you an extension until next Wednesday. Today's lab is a problem set that's due in 2 weeks. Okay, it's a problem set, acid-base problem set. Out of that problem set, you can skip anything that involves KF, which stands for complex ion. It's something I'm not going to cover. All right, yes, no? Okay. All right, so let's do some problems here. This is acid-base chemistry, and I think I should be able to finish this chapter today. So, yeah. All right, so which way does the equilibrium shift in the following reaction, right or left? So let me tell you what's happening here. This CH3COOH is called acetic acid. That's just the name of the compound. And this HCOO minus is called formate. Right, so what's happening here is that this H, acetic acid, acids give protons, so H plus, and when it does, it becomes the acetate ion. And this formate receives, it takes that H plus, it takes that proton, and it becomes formic acid. You see what's happening here, or is this blurry? Right, so anything with an H, usually dissociable H, by dissociable it means it can come off. So that is an acid, and an acid will give off H plus. So this is going to be the acid. When it gives off the H plus, it becomes the conjugate base. So acetate is the conjugate base. Formate takes that proton. Okay, formate takes that proton. Anything that takes a proton, not gives, but takes an H plus, we're going to call that a base. It takes it and it becomes the conjugate acid, Ca. Acid-base chemistry, giving a proton, taking a proton, giving an H plus, taking an H plus. So the question in this problem here is, which way does the equilibrium shift, right or left, in the following reaction? And what do they tell us? They tell us the pKa of acetic acid is 4.76. And they tell us the pKa of acetic acid, is 4.76. And the pKa of formic acid, this is acetic acid, this is formic acid, is 3.75. So which way will this equilibrium go? Okay, how do you know it's in equilibrium? Okay, always check the arrows. Okay, always check the arrows. The arrows will tell you that it's in equilibrium if it's back and forth. And so which way will this go? Which is the stronger acid? Something with a pKa of 3.75 or something with a pKa of 4.76. Okay, so here you must know this. This pKa, this lowercase p, stands for power. Okay, power. So power. So pKa is minus the log of Ka. Just like pH is minus the log of H plus concentration. POH is minus the log of OH minus concentration. Okay, because of the log math, if your pKa is low, that means your Ka is high. Okay, Ka is high means it's a good acid. Okay, if you have $1 million, you're moving forward in wherever. Okay, if your Ka is 1 million or 1 billion or something really, really strong, you're moving forward. That reaction is moving forward rather than back. Okay, so based on this relationship, okay, which do you think is the stronger acid, acetic acid or formic acid? Okay, lower the pKa, stronger the acid. So which is the stronger acid? It's going to be HCOH, formic acid. So which way will the equilibrium go, right or left? So this is going to give an acid, this is going to give the proton more, so it's going to give the proton more, so I am seeing this, do you guys agree with me? I am seeing this moving to the left. Okay, why is it moving to the left? Okay, which is better at giving off protons? Okay. Which acid is better off? Which acid is better than giving off protons? It's the one with the higher Ka, but that means lower pKa. So which is giving off better protons, better ability to give off protons? It's formic acid. So the reaction formic acid is going to give away protons. The equilibrium is shifting to the left. So something you should know here. Okay, so on this exam, you'll have to rank acids. Okay, so when you rank, 5 or 6 or 7 acids, and they give you the pKa or they give you the Ka, you're going to have to rank it. Okay, so get all of them in pKa's, or get all of them in Ka's, and then rank them. Okay, you can rank them based upon, the lowest pKa, most acidic, or you can rank them based on highest Ka, most acidic. Okay, so this is important. I want you to know this. I think it's also used in the MCAT or whatever these exams. Okay, for the doctors that are going, future doctors in this room. So this has the lower Ka, it's a better acid, so formic acid is going to be better at giving away protons. Alright, let's do this problem here. This is an ice table problem. We did a problem like this before break, on Friday before break. This will also be on the exam. Okay, this is going to be very, very, very common. So once you know this, everything else should come easy. Okay. So what is the pH of a 0.6 molar formic acid solution? The Ka of formic acid is 1.8 times 10 to the minus 4. It's a weak acid. Okay, it's a weak acid. How do I know it's a weak acid? Because it's not these 6. Okay, what are our 6 strong acids? Can anyone tell me? Okay, HCl. What's another one? HBr, HI, another one. Nitric acid and H2SO4, and then HClO4. Okay, so these are strong. Okay, if it's not this 6, then you have to use the ice table. Right? Well, formic acid, actually it's right here, formic acid, it's not one of these 6, it's a weak acid, so we have to use the ice table. So here's the equation for that. HClOH. Okay, you're going to have to write this equation on the exam. Okay, write this equation on the exam. This is the equation for Ka. This specific A is formic acid. This very specific acid is formic acid. So this is our standard equation. H3O plus and formate. Right, so what this means is that if I have a bottle of formic acid, I have a bottle of this formic acid. It's not just HClOH that's in there, okay? It's not just HCOOH that's in this bottle of formic acid, 0.6 molar concentration. Okay, there's some H plus in there. There's some formate, and all of this is dissolved in water. And there's also some formic acid, the main chemical. Okay, the main chemical, but some of that in that water will be H plus, H3O plus, and then HCOO minus. Some of it is going to go this way. To what extent? This extent, 1.8 times 10 to the minus 4, which is the Ka. Okay, usually it's at 25 degrees. Okay, we quote this at a specific temperature. But just also telling you for the test, formic acid is called the acid. Okay, acids give away protons. Bases take the proton, so that's the base. Acid gives away the proton, so it gives rise to the conjugate base. So these two are a couple in the square. And then the base takes that proton, it gives you the conjugate acid. Okay, H3O plus is the conjugate acid. Okay, that's the triangle here. So these are couples. Okay? And H3O plus and H plus is the same. Okay? The way I'm teaching it, it's the same. Okay, so if I say H plus, I mean H3O plus. If I say H3O plus, I mean H plus. Okay? Get that? Yes? So it's the same thing from making things a little easier. All right, now let's solve this problem. They're asking for the pH. This is what we want. Okay. We will have to use the ice table to get that. So ICE, this is kind of what you'll be doing on the exam. This is kind of what you'll be doing on the problem set here. So 0.60 molar. Okay, water is a liquid, so we do not care about it because water is a liquid, so you can just cross it out or do what you need to do. Okay, minus X plus X plus X. Everyone see this? Okay, this will be 0.60 minus X. Just do this on the exam. Okay, don't do anything with water. It's a liquid. Solids and liquids you don't mess with. Leave it. Solids and liquids, leave it alone. Okay. All right, so this is the concentrations at equilibrium, right? So we will plug this into Ka. Ka is equal to H3O plus times HCOO minus divided by HCOOH. Okay, this is called products over reactants. Okay, we do not put solids, we do not put liquids in there. Okay, Ka is given to us as 1.8 times 10 to the minus 4. Okay, at equilibrium, when this thing settles, okay, okay, like a seesaw, okay, you may have some a little bit this way, balance this way, tilt, whatever tilt it may be. Okay, when it's all finished and all done, this will be X, this formate, conjugate base will be X, and this HCOOH will be 0.60 minus X. So that's at equilibrium. Our goal is to solve for X. So X times X is X squared. Excuse me, this is 0.60 minus X. Alright, so 1.8 times 10 to the minus 4 is equal to X squared divided by 0.60 minus X. So here's what I want you to do. I want you to do something called the low ionization assumption. Do you remember this? Okay, we're going to assume X is small. Okay, when we assume X is small, 0.60 minus X will be about 0.60. Okay, this is called the low ionization assumption. Do it. Okay, do this on the test so you don't have to use the quadratic equation. And on the quiz and on your homework. Remember, the threshold is 5%. Okay, I'll tell you more about this 5% number later. So 1.8 times 10 to the minus 4 equals X squared divided by 0.60. This is the low ionization assumption. Low ionization assumption. I'll just write. I don't want to write all that letters. Okay, low ionization assumption. 0.60 minus x is about 0.6. Right, so 1.8 times 10 to the minus 4 times 0.6. Okay, we'll take the square root of that to get x. Basically what I'm doing here is solving for x. What is x? Can we do this on our calculator? Alright, so 1.8 times 10 to the minus 4 times 0.60. And we will square root that, isolating x. That's my square root button. Hard to find. And I'm getting 0.0104 big M. 0.0104 big M. Okay, so what is 0.0104 big M? Super important. It is x. And what is x? H3O plus. Okay, do you guys see this? Okay, let's do it again. Okay, what is this 0.0104 big M that we solve? It is x. And what is x? It is nothing more than our H plus concentration. Okay, let's check our assumption. Okay, check our low ionization assumption. The threshold is 5%. So checking our assumption. Okay, sometimes assumptions fail, so. Okay. Low ionization assumption. So we'll take our x and divide it by the initial acid concentration. Okay, the initial acid concentration. So x, we just found that, is 0.0104. And what's the initial acid concentration? That's the concentration in the bottle. And what's the concentration in our bottle? Is 0.6 m. Okay, 0.6 m. Or 0.6 times 100 to get it into a percent. What is our cutoff? Okay, it has to be less than 5%. Okay, less than 5%. Less than 5%, we're good. Over 5%, this is a little bit too strong for our assumption. But if it's less than 5%, it's a weak acid, and this assumption is good, and it's valid. So here we go, 0.0104. Bless you. Divided by 0.6. Okay, times 100 is 1.7%. Yeah, way less than 5%. Okay, our assumption is good. Let's finish with our right answer, or with our answer. Okay, cutoff is 5. So, on the exam, I'm going to not have you do the quadratic. They all should be less than 5%. So you can go ahead and use this assumption. Okay, we're not done. A lot of people will end here. The question is, what is the pH? So let us do our pH. Okay, pH is minus the log of the hydrogen ion concentration. Okay, which is 0.0104. And remember, you're not allowed to put units inside the log. Just letting you know that. Okay. So what's minus the log of 0.0104? How do we do this on our calculator? Minus log 0.0104, close those parentheses. 1.98 is the answer I'm getting. 1.98. And that should be our answer. What's the pOH? Okay, you'll subtract 14. Okay, but it's asking for the pH. Right, so this is what I want you to do for the exam. Okay, quiz, exam. Okay, maybe your future chemistry classes, whatnot. All right. This is how you do it. Okay, it's less than 5%, so the assumption is valid. If it was greater than 5% by whatever means, and we did an example of that last week, I do not know if you remember, but if it's greater than 5%, you can't do this, you have to use the quadratic. Okay, you'll have to use the quadratic here, but I'm not going to have you do that. Any questions or comments? Right, so something like this will be on the exam, okay, on test. Okay, on test, on quiz, okay, until we finish the class. And this is what you're going to do. Okay, I also want you to write this equation. Okay, this equation to me is important. Okay, so write this equation also. This is how you do that problem. All right, shall we move on here? Yes, no? Okay, last 10 or so minutes of class, actually last 15 minutes of class. Let's finish up these last couple of pages here. So, wrap things up. Yeah, so yeah, make sure you also know this Kw is equal to Ka times Kb. So if you take the Ka reaction, if you take the Kb reaction, add them up, you multiply the constants, you'll get Kw. Okay? And Kw is 1.00 times 10 to the minus 14. This is a good equation to have in your tool belt. Okay? So if you're given the Ka, you can get the Kb. All right, let's talk about polyprotic acid. Polyprotic acids means it's just not one proton, but two protons or three protons. Right? So in our strong acid list, one of the strong acids, if you remember, is sulfuric acid. One of the strong acids was sulfuric acid. But you see, it's the first proton that is strong. It's the first proton. Okay, the second proton, not so much, not as acidic. The first proton comes off easy. The second proton, not so easy. Okay? And here's the equation for that. This is considered strong, so actually what I really should do is make this, one direction, one arrow going this way. And that's how it is, okay? So this is strong. You would think the second proton is strong, but it's not strong. Okay, it's not strong. So this is the trend I want you to know. Look at this example with me. This is called phosphoric acid. And this is called H3PO4. How many of you drink Coke or are big Coke drinkers? You've been to the Coke factory in Georgia? No? Okay, the first proton comes off. Okay, the second proton is weak. The reason why I'm asking about the Coke factory and Coke in general, because Coke has a lot of phosphoric acid. Did you know this? Okay, you can look that up in the ingredient list, phosphoric acid. And also, phosphoric acid can clean things. It's a cleaning agent. So you'll actually see YouTube videos of people cleaning their toilets, cleaning the ovens, cleaning the engines with what? With Coke. Okay, because it's the phosphoric acid cleans that. So if you immerse an egg, a hard-boiled egg, in Coke, and then I think if you wait 2 or 3 days, the Coke shell will the egg shell will crack. You can remove the shell and have a hard-boiled egg. So all of that is the phosphoric acid in the Coke. So phosphoric acid is interesting because it's an acid. In this example, it can give away not one, not two, but three protons. You see the H3PO4? H3PO4. So the first proton comes off with a Ka of 7.5 times 10 to the minus 3. Okay, so that's weak based on the 10 to the minus 3. It has a pKa of 2.12. Okay, what else can this do? This H2PO4, it can give a proton itself. Okay, that's what we have here. That is what we have here. And it gives off its proton and it becomes this. I'll put it in orange. But I want you to know the second proton is 6.2 times 10 to the minus 4. pKa 3.21. Remember our trend. Okay, higher the pKa, lower the Ka. Okay, lower the pKa, the better the acid. Okay. So H3PO4 is a better acid than H2PO4 minus, right? Because the second one has a pKa of 3.21. Okay, look at this one, HPO4 minus 2. This can give off a proton. Okay, and when this gives off a proton, the last proton, it becomes phosphate. But that proton in HPO4 minus 2, look what it comes off at. It has a Ka of 4.8 times 10 to the minus 13. 10 to the minus 13. Do you think this is a good acid, HPO4 minus 2? And why do you think it's not a good acid? Because the Ka of that is 4.8 times 10 to the minus 13. 10 to the minus 13. Okay, that is a very, very small number. So this proton probably won't come off. 7.5 times 10 to the minus 3. That's small, but it will come off. Okay, so this is the trend. Okay, so the best acid is H3O phosphoric acid. The weakest acid is HPO4 minus 2. This is the trend. Okay, the first proton is acidic and subsequent protons are less acidic. Okay, so let's write that down. The trend. Okay, for polyprotic acids. Polyprotic means more than one proton. For polyprotic acids, the first proton the first proton is acidic. Okay, 7.5 times 10 to the minus 3. Okay, the first proton tends to come off easy. It's very good, very acidic. Okay, the second proton, the third proton are not as acidic. The second proton, 6.2 times 10 to the minus 4, not very acidic compared to the first one. The third proton, 10 to the minus 13, okay? Not a good acid, 10 to the minus 13. Okay, so the second, third, subsequent protons are less and less and less acidic. Okay, the second proton and third proton are less and less acidic. The second proton, the third proton are less and less acidic. This is what we see for polyprotic acids. Okay, more than one. So they call phosphoric acid triprotic. Tri means 3. So it can give off 3 protons. Something like sulfuric acid is diprotic. Di means 2. So sulfuric acid can give off 2 protons. So this is something I'd like for you to know. The trend. All right, so just know that in the, the back of your mind, and And let's finish up here, the last couple of pages. There is a problem here. I'm not going to go over it. And, this is something that you can watch a video of if you have time. If you know how to do this type of problem, the examination problem is a piece of cake. So I'll let you decide based on your time and schedule if you can watch it. But this is oxalic acid is a diprotic acid. So diprotic acid, if you need to calculate the concentration of each of these species, you need not one ice table, but two ice tables. Okay, and first ice table for the first proton, second ice table for the second proton. So that's the only thing, okay? So you need an ice table for this proton, H2C2O4. Then you need an ice table for this proton, HC2O4. Right, so I'll let you watch that video, and just to save some time, watch it. If you can do it, the test exam one will be very easy because that's only one ice table. This problem requires two ice tables. So check that out when you have the time on Canvas. If not, you can use the study guide that I have on Canvas. Finally, strong acids. Okay. Strong acids, there's 6 strong acids, but I just want to bring your attention here. Okay, what's inside this box? Okay. If you look at the halogens, okay, halogens are group 7 or 7A. We have hydrofluoric acid. We have HCl, which is part of our 6 strong acids. We have hydrobromic acid, which is part of our 6 strong acids. And then we have HI, hydroiodic acid, which is part of our 6 strong acids. Okay, why are these acids so strong? Okay, it has to do with electronegativity. Electronegativity. What is my definition of electronegativity that I'd like to share with you? Okay, it's like a vacuum cleaner. What does a vacuum cleaner do? Okay, pulls. It pulls. Vacuum cleaners pull. It has a sucking power. So this pulls. So back to HCl. Okay, Cl is going to pull. This is not an equal bond. Okay, this is not a 50-50 bond. Okay, the Cl pulls. Okay, the HBr pulls. And it pulls. Let's write HI. It pulls until eventually the H plus is gone. Okay, eventually the H plus gets ejected. It goes out, goes away. Okay, all right. So particularly with the halogens, which are electronegative, as you go down, these acids become more acidic because the pull is more stronger. Okay. I mean, look at it this way. This HCl is a bond, but it's not a fair bond. I want to try to convey to you or convince you that this Cl pulls, and it pulls because of its electronegativity to such an extent that it pulls it all the way, that electron density all to itself, giving away an H plus. Okay, same thing with the Br. You have a bond here, but I want to convince you that Br pulls to such an extent it takes all of that electrodensity with it, and it becomes H plus. Okay, same thing with Hi. Okay, I minus, that bond. It's a bond that you see here, but the I pulls. The iodine pulls. It pulls, and then as it pulls, it takes all of that electron density to itself, and then the H plus just goes away. Okay, so this is the basis behind, at least for the halogens, why they are strong acids. Okay, there's such a strong electronegativity associated with it. Just some information that I'd like for you to know. Okay, pull. The strong acids, HCl, HBr, they're strong because the atom is electronegative. They pull. All right, with that in mind, let's answer this question here. Which of the following acids is weaker? HClO2 or HClO3? Which one would be the weaker acid? Well, which one would be the stronger acid? One with 3 oxygens or 2 oxygens? Okay, this has 2 oxygens. Okay, so which is more electronegative? The one with 2 oxygens or 3 oxygens? 3 or 2 oxygens, which is more electronegative? Okay. That's the one that's going to have 3 oxygens, right? Okay, 3 oxygens has more pulling power than 2 oxygens. So, with something that has 3 oxygens has more pulling power, it means this H plus can come off more easier. So what makes it a strong acid? Well, the 3 oxygens pull. Okay, the 2 oxygens less pull. So this would be a weaker acid. Three oxygens, more electronegative, more pulling power. More pulling power means that H plus can just go away. Okay, it pulls on that bond. The 2 oxygens on HClO2, okay, less electronegative, less pull. Less electronegativity, less pull, weaker acid. More electronegative, more pulling power. Think of electronegativity as a vacuum cleaner, sucking on that bond, pulling it to itself, pulling that bond to itself. Okay, more of those electronegative atoms around, more pull, the H plus comes out. And bless you, it becomes a better acid. Okay, the last 2 things really quickly here. Look at some of these reactions that we have here. We have sodium oxide. If you put it in some water, we get sodium hydroxide. So you can actually get an oxide and make a base. Okay, this is all about acid-base chemistry, right? CO2, you know we breathe out CO2, right? Okay. We take in oxygen, the lungs breathe out CO2, we breathe out CO2. So this reaction happens in our lungs, so we can take a gas and make an acid. This is called carbonic acid. And this is actually found in our blood, okay, and it's found in our lungs. Okay, I know this. So from a solid we can get a base, from a gas we can get an acid. Okay, from a gas we can get a strong acid, nitric acid from N2O5. So some interesting reactions that you can get. Okay, oxides can give rise to a base. Oxides can give rise to an acid. Okay, so yeah. Giving rise to acids or giving rise to bases. Oxides can give rise to an acid or a base. Right, so just something I think, I mean, to me it's interesting. CO2 gas that we breathe out in our body gets converted to acid. This is a weak acid, by the way. Sodium oxide gives rise to a base, bless you. Okay, this is a gas, N2O5 gives rise to an acid. All right, I'm not going to test you on this, but if you take organic chemistry, there's something called Lewis acids and Lewis bases. What I've been teaching you now is Brunstad acids and Brunstad bases. Okay? This is the final thing here, so just give me 2 minutes. Brunstead acids and Brunstead bases give or take protons. Right? Giving or taking protons. That's the whole thing. H plus give, H plus take. This is your examination, essentially chapter 15. Lewis acids, Lewis bases give or take electrons. Okay, give or take electrons. A Lewis base is an electron, I guess, giver. How do you put it? Giver. Okay, so usually it has a lone pair. Okay, so we're talking about electrons, not protons, okay, which is what I've been teaching you. Lewis base is an electron donor, okay, electron giver, and a Lewis acid is an electron taker. Okay? It's an electron taker. Okay, so it does not have lone pairs in its structure. So, you know, this is for the organic chemistry people. Okay, Lewis acids and Lewis bases, not Brunstead acids and Brunstead bases, which is what basically I've been teaching you. Okay, we're talking about the transference of protons. So that's a wrap of chapter 15. I'm going to assign the homework for chapter 15, and let's make it due next Wednesday for 10 points. All right, so if you want 10 points, turn in your chapter 15 homework. Everyone gets 10 points. Just turn it in. Let me write that down. Okay. Due next Wednesday, 10 points. No lab. It's the problem set. Start working on it. Okay, get with your groups. I'm inviting you to work together. Turn in your own work, but work with your lab group to finish up those problems. Watch the video that I made, and use the lecture to help you get through those problems. Okay, homework 15 due next Wednesday. Thank you.